All right, let's go ahead and get started here, people. Okay, so there's some different sorts of problems here. We have power. What's the formula for power?
I got you.
Yep.
It's the top number, the 19.
Yeah, but what's the formula?
190,000 divided by.
Okay, but what's the formula for power?
It's work divided by time.
There you go. Okay, and in this case, you want to find how much work, right? This one on top here. So we are going to rearrange this equation and use power multiplied by time to get work. Yep. Got it? Okay, so we have power, which is 190,000 watts. Multiplied by 9 seconds. So then that's going to equal the work. Bringing up my little calculator friend here. 0, 1, 2, 3 times 9 is 1,710,000. And work is in joules. Okay? Everybody got it? No big deal. Okay, so now another engine reaches its top speed from rest in 7.5 seconds and is able to perform this much work, okay? So this is a pretty straightforward application of power. So we have 250,000 joules. That's our work number, divided by 7.5 seconds. And anybody get a good answer for this? Yeah, Daniel.
Is it 33,333 watts?
Lots of threes, right? Okay. Okay, so now this last one here, or this not the last one, but the last one of the original three, if a runner exerts 350 joules of work to make 125 watts of power, how long did it take the runner to do the work? All right, well, we go back to this. And actually, it's kind of helpful to think about this form of the equation here, because we said power times time is equal to work, right? So, if we want to get time, we're going to divide both sides by power. Therefore, time is equal to work divided by power. Right? All right, what's everybody so silly about today back there?
Somebody was looking.
Somebody was what? Okay. Hey.
It was dark skin.
So 350 divided by 125 watts is how much time? Yeah,
2.8 seconds.
about 2.8 seconds or so. Okay? Questions on that? No big deal? Pretty straightforward calculations. All right. So now we have a girl pushing her little brother on a sled with a force of 300 newtons for 750 meters. Okay? We know that work is force times distance. So, this first one at least is pretty straightforward. You just do work, which is, or force, which is 300 newtons, multiplied by a distance of 750 meters. And how much work is that? Anybody get it? Oh, come on. Okay. Did you get it? No, actually. Good. 225,000 joules of work. Okay. Now, this next question, what you might be asking yourself when you read this next question is, okay, well, used by whom, right? We talk about the little brother. The little brother didn't use any work, didn't use any energy. The only thing involved here would be the girl using the energy. And how much energy did she use? Now, it seems a little bit confusing, but I'll give you a hint. If you're doing another calculation, then you are probably wrong. Same thing, right? Because when work is done, the only way we can do work is by using energy. That's why you're tired after doing work. Because you use energy. Right? So, if work is done, if something is lifted from one place to another, that energy has to be injected into the system. It doesn't just happen on its own. So, if there was 225,000 joules of work done, that means somebody or something had to do it. In this case, the little girl had to use 225,000 joules of her energy to do it. All right? So, what the heck is going on over there? Huh? Better not be taking pictures of me. Now, okay. Letter C. How much power does she use if it takes her 25 seconds? How do we do this? Her power is work divided by time. Okay? Our work was 225,000 joules. Our time is 25 seconds. So how many watts is that? Yeah.
9,000 watts.
9,000 watts. Good. All right. Now, in D, we are reducing the time from 25 seconds to 10 seconds. So before we even calculate this, is power going to go up or down? Up. right? Because it's time, and that what this is illustrating is that the relationship between power and time. As time goes down, power goes up. Because power is all about doing things faster. Somebody does something with power, that means they do it quickly. Right? They have a fast use of that work, energy. So, we have divided by 10, same value, but divided by 10, which is obviously going to be 22,500 watts. Okay? Because it's just divided by 10 instead of 25. Okay, questions on that? And you know that when you're watching, like if you watch an athlete, you can see an athlete that has more power than others, right? Because they jump higher, they move faster, they're quicker. That's power. Again, it's not about time. It's not about just the work energy. All right? Okay. Now, this one is a little bit more thought-provoking. What do you think about this one? You got a 75-kilogram man pushing a wall 500,000 kilograms for 250 seconds. That's a long time. That 75-kilogram man's going to be tired. It's a long push. So, Mr. Hensley, you look very contemplative today. Thinking. Just contemplative thinking. How much work does he do on the wall? What does work equal? Force times distance, right? What's the distance that changes? Right. The change, if distance is 0, what's work? 0, right? It doesn't move, so it's 0 work. Now, remember that there's a scientific way of talking about work, and then there's like the everyday work, right? That's why I kept saying this guy's really tired, but he doesn't do any work because the thing doesn't move. Obviously, right? 500,000 kilograms. That's a lot of weight. That's 1.2 million pounds. So, he's not going to be able to do much with that. But if there's 0 joules of work done, how much energy did he use? Don't let your biases change your thinking. Yes. 0. Right? Because if he put 0 energy into the system, which he did, then there's 0 energy used. Now, that doesn't mean that he himself didn't use 0 energy, but he didn't put any of that energy into the wall because it didn't move. All right? Again, just think conceptually about this. Okay? And looking at the power equation, if there's 0 work used, what's the power? 0 watts. Right? Has to be. Okay? Questions on that? All right, good. Now, I know that the question that everybody is thinking is, oh, gosh, we have, I guess, Tuesday of next week, we have exams, yes? Okay? So, and probably even before the middle of the last semester, so just tell me, so we can make a study guide of the, okay, well, let's talk here. We have kind of chatted amongst the faculty and whatnot, and our Mr. Numbers has given us some leeway in terms of how we do the exam. So what I want to do is, because I think that this is a crucial unit for the first semester, if you all understand, and I didn't get a chance to test you on this in person. So what I want to do is I'm going to make the semester exam basically kind of an intensive test over this unit. So I'm not going to do it over the other stuff on this semester. So it's going to be focused on this unit. Okay. So what? So hopefully that's a good thing. Yes. Well, I'm gonna get in detail about what I think you all should do on Wednesday. I'm gonna remind you on that, and also go over the most recent the take home. I'm almost done with that. I got the other classes date. I'll have you guys done hopefully by this evening. And overall, I think it's okay, but you know, a lot of people are still a little bit confused over some things. So we need to make sure that we get all that ironed out, and then we'll talk about what you guys need to know for Tuesday. Right? Now, see, and here's the other debate that I'm having in my mind is, like, I know I'm going to use it for the semester exam grade, however, what I'm thinking about doing is also using it in part as a grade for like a final test grade for the quarter, if people do well. So basically, if everyone does well, then it would count twice. The exam. So it would count for the exam, but also like as a test grade for the second quarter. So basically, if you have a good grade right now, you probably don't want that option. If you don't, then you want that option. Right? I have this idea. I thought maybe I would see how much of gamblers you all are, and like you have to commit before you take it. I want it to count twice, or I don't want it to count twice. Right before you take it. That would be kind of fun, right? What? So, yes. Oh yeah, yes, good thought. Go ahead. Okay. All right, Connor. I know it's a temptation. Just take a little, please. Okay, so that's kind of the information that I want you all to know for the exam. Today you'll have your last homework assignment for the semester, which is on mechanical advantage. I think that's it as far as the downside. Anybody have any questions? Yes. Yeah. There. Okay. So, if there are no questions, go ahead and get these notes right here, and we'll finish this up. Yeah, that's going to be at the end of this. Yep. This is my plan. All right. So, the last day of our remote learning, we were talking a little bit about these machines. Now, in talking about these machines, we also talked about this mechanical advantage. Now, mechanical advantage is this way of helping to multiply a force sometimes, right? Because, like, if you're using a machine, maybe it turns 2 newtons into actually 10 newtons of usable force. Or sometimes it involves a change in direction of the force, which is also valuable, which is like a pulley system. Right? So you can use the same amount of force you use pushing something that's pulled up instead of out. And sometimes there's not a great increase in the amount of force that's produced, but because of that change of direction, that's what makes it valuable. It just depends on the machine. But the idea is that it changes the way that the work is used. Now, we talked about a few of them. Probably the biggest one we talked about was the inclined plane. And the inclined plane is used as, and you have to remember, when you think about the inclined plane, this formula for work. Work equals force times distance. doesn't matter how the chair got there, because the potential energy that it has when it's out on the table is equal to the amount of work that's required to get it there. Because you have to put work into the system to get that potential energy, and however much work you put into the system is how much potential energy you get. All right? Now, the idea of the inclined plane is, okay, if we have the same amount of work to get this chair up here, whether we take it straight up, or let's say we have it over here, and there's a ramp, and we push it all the way up this distance, and put it up like that. Although the distance increases, the force is going to change because the work is the same amount regardless of the distance. So if D increases, mathematically F has to go down, right? Because if this is 10, and you start off with a distance of 2 meters, then this force has to equal 5, right? But if we have work is 10 and the force here, and let's say we change it to 10 meters, now what? Now how much is the force? 1, right? Okay, so as we increase the distance of that ramp to get it up there, then the force goes down. Now, it might take it longer to do it. It might be more of a pain to do it that way. But if it's really heavy, then that's worthwhile, right? We don't worry about having ramps here to put the tools up because it's just not that hard to do. Yes.
So if you have a ramp, the work stays the same no matter if
Yep.
you don't have a ramp or not? Okay.
Right. It's just how much force is required. You decrease the distance, you increase the force required. You increase the distance, you decrease the force. Okay? Now, for light objects, there's no reason to have a ramp. But if something is really heavy and you couldn't move it otherwise, or you need to do it a lot of times, it's going to be worthwhile to do because there will be less of an exertion on the human involved typically. And I gave this example before of how the pyramids came to be. Because those big blocks of sandstone are hundreds of tons heavy. Yes. Yeah. So if you are doing that, with the humans there, they can't pick that up. But what they can do, and the theory is that they did, assuming you don't go along with the aliens that brought the pyramids and put them down theory, is that they built a system of ramps. So instead of bringing the blocks straight up, you bring them all this extra distance around here with the ramp, and then you're able to get it. It'd still take dozens of people to do it, but it's doable that way. All right. And typically they would, I think they put them on rugs or something, and get up. You have a bunch of friction with the ground on those ramps. But that's the way that it was done. I mean, keep in mind these took, about 100 years or so to make. So it wasn't obviously not an easy task to do. But anyway, so that's the way that inclined planes work. And you see the mechanical advantage is taking the length of the incline divided by the height. Right? So the longer the ramp is, the less force that's involved. The better the mechanical advantage. Because the height is going to pretty much be the same regardless of the length of the incline. You can make different lengths of ramps, and you can kind of just logically see, obviously that's going to be harder if the ramp is shorter. Right? So, that's how we do that with a ramp. A wedge. The wedge is just a special case. These next two are really just special cases of inclined planes. But if you take a blade, one day I didn't bring my knife. Oh well. If you take a blade, it's basically increasing that distance that's required to go into the object or whatever. By doing so, you're making each little bit of it easier to do, right? And in order to get something inside of, like a piece of wood there, you need to have sufficient pressure at the surface, right? And I talked about this, the pressure is force divided by area. Now, the area that's involved then will be the cutting surface of the blade, right? Like you have this knife here, this surface right here is what cuts into it, so that's the area that we worry about. So that's why we sharpen blades. Because as we make that area smaller, what happens to the pressure? Mathematically, what happens to the pressure as the area gets smaller? It increases, right? Now, to get a better visual of this is, if you think of somebody, something like in this massage, whatever, people walking on other backs and stuff. You can imagine someone doing that in their bare feet versus in high heels. Same person. You're probably not going to want them to do that in high heels, right? Because you get a decrease in area, you're going to vastly increase the pressure at each point where they do it, right? The same thing with getting an injection with a needle. You want to have a nice sharp needle if somebody's going to give you an injection. Because this point here is what's going to go into your flesh. And if the area is bigger, if it's dull, then what has to increase? The force, right? So instead of somebody coming up and doing a little shot like this, they go, and they do the shot. Probably not what you want, right? Because it's going to be more tearing into the flesh. Plus, with the blade bigger, it's going to push your flesh out more. It's going to cause more damage. So, you don't want dull needles. Okay. You also don't want dull knives. Right? Remember that a sharp knife is safer than a dull knife. And don't forget that lesson. Because with the dull knife, you have to push harder, and it doesn't get into the surface as easily, so it's going to slip more easily. And if it slips, then your chances of getting cut are going to go up. Right? Now, for sure, the sharp blade could cut you better than a dull blade, but you're far less likely to get cut with the sharp blade than you are with the dull blade. Right? So make sure you're using knives, make sure they're sharp. That's important. Right? So, and then here the screw is just another example of this inclined plane. Again, I always think of the screw is kind of like this spiral staircase here, going into the wood, because that's the distance that has to go into the wood. It's going to increase the distance, so it's a lot easier for you to put the screw in than it is to hammer the nail in, because the distance is greater. Right? And there are other advantages to that. It's going to typically hold together the stuff better with screws, but the idea is that it's going to make it easier to do. Okay? Now, levers. The most important part to understand with the lever is to understand what a fulcrum is, which is just a pivot point here, and where the fulcrum is. Right? If it's in the middle here, then this is a first-class lever. Right? Also, recognize that this right here with the mechanical advantage. Right? It is the distance to the output, distance to input divided by distance to output. So, just looking at this, and this is the distance of the fulcrum, by the way. You want to have a bigger distance of the input and a smaller distance of the output to get a better mechanical advantage, which is what you want if you're using it as a tool. All right. So our first class lever is pretty much anything that you use to pry stuff out. You know, you've ever had to like pry nails out, anything like that. That's the first class lever. The feeder cotter is the first class lever. And that fulcrum, you want to get, if you're prying something out, you want to get that bar as close to the nail as you can to get a good grip on it, and because it gives you better mechanical advantage when you're prying it out. All right. The other part of that is the longer the crowbar or hammer handle, the better, because it's going to be a bigger distance to the input force and give you better mechanical advantage. So if you have like a little crowbar, you can't pry something out, just get a longer one, and you probably have more luck with it. Because that's going to give you more mechanical advantage. You're going to convert more of your force into actually prying force. Okay? This is also true with the wrenches. A wrench tends to act like a first class lever. So the longer the handle on the wrench, the more torque that you're going to get, and the better you're going to be able to move that object. All right. First class lever, again, input force to output force. That's what we're looking for. If the fulcrum is in the middle, it's always first class. Okay? Now, you put the fulcrum on the end, and both forces are going the same way. If the output force is in the middle, it is a second class lever. All right? Now, you'll notice, like with the wheelbarrow here, the force is required to push the object up. Okay? And also the tub of the barrel is always pretty much right over that wheel, because the wheel is the fulcrum. You don't want to push this up here because it's going to make it harder to hold it, because you're not going to get as much mechanical advantage because you're increasing that distance to the output force. Also, you want to have nice long handles back here, increasing that input force range. Right? You wanted to make a better wheelbarrow, make longer handles. Okay. Pretty much all you can do. You can't get too close to that wheel, otherwise it wouldn't work very well. But all right. Oh, another thing is the door is a second class lever. If you've ever noticed that the handle's always opposite the hinge, right? Because that's the input force, and the output force is here, and the fulcrum would be the hinge. But if you try to push closer to the hinge, it's harder to move the door than it is where the hinge is. Because, again, you're decreasing that input lever, making it harder to move. All right? Questions on that? Everybody got that? Not that big of a deal. Just make sure that you're aware of these and how they're different. Okay? Now, the third class lever, this is probably the worst in terms of mechanical advantage, because you'll notice that the input force is closer into the fulcrum, so it doesn't move stuff nearly as well as a first and second class lever. However, this is good for changing directions. Right? Like if you're raking or sweeping or something, and you want to move an object in a certain direction, and it's not necessarily a heavy object. If you ever try to rake up something heavy, it doesn't work very well. Right? You better pick it up, because you're not going to get a ton of force with it, but it is good and very good and efficient to change the direction of the object and where it's going to go. Right? But if it does get tougher, like if you're raking here, then he would just kind of choke down on the pole, so that he can like tear something out of the ground or whatever. You have to get closer to that rig and to get more force involved, because you're increasing the distance of the input force to the fulcrum. All right. Okay. And yes, you kind of go through here. I've listed out what type they are, Make sure you understand why whatever type is given. Look through those. I think that stuff is fairly straightforward, but if any of it confuses you, then just let me know. All right. Left two more types, and that'll be it for today. We have the wheel and the axle. This is common in the way that cars are set up, right? Because you have the axle for both sets of tires, and the axle fits into there. And then if you want to have a car or a vehicle with more power, typically you're going to get bigger wheels. Because if you look at the mechanical advantage, the radius of the wheel is one of the determining factors, and that is positive determining factor. The bigger the wheel, the more mechanical advantage you get. Right? If you look at like some stuff like off-roading kind of cars, typically they're going to have a little bit bigger tires because you want to have more power than speed to get through mud and all that other stuff that they might run into. The other is, and this is a little bit you got to be careful about because it's the radius of the wheel to the radius of the axle. Now you don't want to mess with that too much because you start getting a thinner axle, what happens? Just logically, engineering-wise, what's going to happen? If you get a thinner axle, it's probably going to break, right? At some point, it gets so thin that you start running over things, you break the axle, and that's obviously not good. So you can make it as thin as up to a point, but engineering-wise, you have to worry about kind of those different forces that are going on there. You don't want to break that axle. So the primary way that you're going to change that with an automobile or any kind of machine tractor is to increase the size of the tire. If you think of a tractor has a huge wheel in the back, right, to get that power as it moves through the field, which is really what it wants to do, or pulling things and whatnot. So, all right. Any questions on that? Pretty straightforward stuff. No big deal. Big wheels, little axle. Mounting the pulley. Now, this works by the same philosophy, the same principle, force and distance. Okay, and we said in the inclined plane, as the distance increases, the force goes down. So, if you look at these here, the pulley is dependent upon the distance that the rope has to be pulled through. So, you look at these, and which one, in which case, does the rope have to go through bigger distance to pull the weight? Think about it. Yeah.
Would it be figure 5?
Yeah, the most complicated, right? So as these numbers of gears go up, it becomes easier to pull because you have a greater distance of rope, a greater length of rope that you're pulling. So that's how you tell the mechanical advantage. Got it? I think you were asking about that. I said that was one because there's one little circle gear. You just count the gears up, or the ropes. Like for example, like this one, you could either take 5 gears, 6 gears, or you can count the number of times the rope goes around. 1, 2, 3, 4, 5, 6. That has mechanical advantage of 6. Yes. Right. So if you're pulling on that rope with 10 newtons of force, you can pick up something that is about 60 newtons. Because you're going to make your force 6 times what it is. Right? And this is like 4, this is like 2, 3. Right? Okay? You see this one here? This is another one with 4. 1, 2, 3, 4. And that's all you do for the pulleys. Just count those ropes that are involved. All right? Okay, questions on that? Yes?
So, if you don't have a visual, how do you calculate?
You can't.
Oh, okay.
I mean, unless it says a pulley with 5 gears, then it's just, well, okay, it's 5. All right, any questions on that? All right, so in your homework, you'll see that there's a bunch of questions on mechanical advantage. There's even some more description in there. So look through those. I think that you'll find those problems really aren't that difficult to do. You kind of get the gist of it after the first one or two of them. But if you have questions, let me know. Otherwise, next time we get together, we'll really get into this. What you need to know for the exam. And then that'll be it. Okay? All right? That's all I got for today. Hey, so by the way, we're coming back. I know everybody's like, okay, well, all these cases go around. Stay where you are until the bell rings.